Deep beneath the Earth's surface, hidden treasures lie waiting to be discovered. For centuries, humans have searched for gold, diamonds, and precious minerals using brute force, heavy machinery, and complex geophysical surveys. But what if nature has already provided us with tiny, tireless workers who have been quietly mapping these hidden riches all along? In some of the most mineral-rich regions on the planet, scientists have made a groundbreaking discovery that challenges everything we thought we knew about treasure hunting. The unlikely heroes of this story are ants and termites. Yes, those very creatures often crushed underfoot have been unintentionally mapping hidden gold deposits, diamond indicators, and mineral-rich zones for millions of years. These insects may not carry pickaxes or wear helmets, but they are some of the most effective prospectors alive today. The science behind this phenomenon is as brilliant as it is simple. Termites, for instance, build extensive tunnel systems that stretch meters below the ground. As they dig, they carry up soil from deep mineral-bearing layers, forming surface mounds that act like natural core samples. Ants do something similar, often targeting mineral-rich zones for nesting due to thermal and moisture preferences that correlate with certain rock types. But what makes this method so powerful is its sustainability. Traditional mining exploration often devastates ecosystems, clearing forests, polluting rivers, and consuming enormous resources. In contrast, studying insect behavior allows for non-invasive, low-cost, high-accuracy prospecting. Where ants dig, clues emerge. Where termites build, secrets rise to the surface. Experts have begun analyzing not just the mounds, but the insects themselves. Termites that ingest soil along with decaying organic matter often swallow mineral fragments, especially gold. Because gold is indigestible, these particles pass through their systems and end up embedded in their waste. Under microscopic inspection, researchers have found gleaming gold dust in termite droppings. It's Nature's assay report, built 1 grain at a time. Beyond gold, this method also points toward possible diamond indicators. Certain ant and termite species bring up kimberlite minerals, rock types associated with deep earth diamond formations. If fragments like garnet, ilmenite, or chrome diopside are found in or around a mound, geologists can infer a high probability of ancient volcanic pipes beneath the area, pipes that might still hold undiscovered diamonds. One particularly revealing sign is the color and texture of mound material. Soil with a reddish hue, dense clay consistency, or visible glints under sunlight often signals the presence of iron oxides, mica, or quartz, all of which may accompany gold-bearing formations. In the field, experts have demonstrated that just by collecting a handful of this mound soil and washing it in a simple pan, heavier minerals settle at the bottom. In several documented cases, gold flakes, sometimes barely visible to the naked eye, have appeared in the final layer. What makes this even more exciting is that anyone, not just large mining companies, can apply this knowledge. A simple field kit, a magnifying glass, a pan, a magnet, and basic soil analysis tools can turn an ordinary explorer into a modern prospector. What was once hidden in the earth becomes legible through observation, patience, and strategy. This isn't just a scientific breakthrough. It's a return to how nature intended us to search, not by tearing the earth apart, but by reading its signs. In many indigenous cultures, there are oral traditions of observing insect activity to find metal-rich soils. What was once considered myth is now confirmed by modern geology. These ancient observations were not superstition. They were empirical wisdom passed down through generations. To understand the full potential of insect-guided mineral exploration, we must look at how these creatures interact with geology on a deeper level. Unlike machines or tools, ants and termites operate in harmony with the Earth's conditions. They don't guess where to dig. They follow gradients of moisture, temperature, and chemistry that often lead them directly to the same areas geologists seek, regions with mineralized bedrock and geochemical anomalies. When termites dig, they sample rock and soil from layers that might be several meters below the surface. This is significant. Traditional sampling at such depths requires drilling rigs, high costs, and complex logistics. But termites bring these materials up for free, in small but measurable quantities. A single mound, when properly sampled, can contain enough mineral indicators to suggest a hidden deposit, if one knows how to interpret the signals. One of the first steps in analyzing a termite mound is assessing its structure and material. Mounds that appear unusually tall, wide, or densely packed are often built using heavier, mineral-laden soils. The color and consistency of the soil can also provide immediate insight. Reddish or dark brown hues suggest iron oxides. Fine-grained, tightly compacted layers may indicate clay minerals formed near hydrothermal activity. In areas where quartz veins run underground, even fragments of crushed quartz may appear in the mound walls. By collecting and testing samples from multiple mounds within a certain radius, a prospector can start to build a map of subsurface activity. If several nests show traces of the same minerals, it's no longer coincidence. It becomes a pattern, one that can point to a deeper source feeding the surface with clues. What makes this approach even more compelling is its effectiveness in remote, unexplored, or heavily vegetated regions where traditional geophysical equipment struggles. Ants and termites don't care about jungle canopies or rough terrain. They build wherever the subsurface supports them, and that often includes areas rich in minerals like gold, copper, and even uranium. By following them, humans can gain access to geological intelligence that satellite imaging alone can't provide. There's also growing interest in the biogeochemical analysis of the insects themselves. Researchers have collected termites directly from mounds, frozen them, and studied the metal content in their bodies. Gold particles have been discovered not only in their digestive systems, but also embedded in their exoskeletons. The insects, in essence, become tiny mobile sensors, absorbing and carrying microscopic fragments of buried metals. This opens new possibilities for low-impact prospecting. Instead of disturbing the land, samples can be collected non-destructively. Soil from nests, insect bodies, and even termite droppings can all be tested using portable field kits or basic lab equipment. When demonstrated in the field, the reactions are always the same: surprise, excitement, and curiosity. Most people never imagined that such small creatures could be carrying evidence of massive underground wealth. Another crucial observation lies in colony distribution. Ant and termite colonies are rarely random. Their layout often follows linear patterns across a landscape, forming subtle paths or bands that align with underground features. By mapping these colonies over a wide area, explorers can detect the edges of fault lines, mineral veins, or even ancient volcanic activity. This is especially useful for diamond exploration, where kimberlite pipes, vertical shafts of volcanic rock that transport diamonds from deep in the earth, can be pinpointed by the trail of mineral indicators that surface-dwelling insects unknowingly reveal. Take, for instance, the discovery of chrome diopside fragments in certain ant mounds. This rare mineral is one of the strongest markers for diamondiferous kimberlite. In regions like Botswana or Siberia, ant activity around diopside-rich soils led to further investigation, and in multiple cases, full-scale mining operations followed. These aren't isolated stories. The science is reproducible, and the logic is elegantly simple. If an insect can reach the mineral layer, it will eventually bring it up. But perhaps what makes this method so transformative is how accessible it is. No heavy machinery, no destruction, no high-cost surveys, just observation, mapping, and smart sample collection. For anyone passionate about mineral hunting, from weekend hobbyists to serious prospectors, this technique offers a real edge. Once a prospector understands how to identify mineral-rich mounds and insect behaviors, the next step is creating a practical field strategy. Unlike traditional exploration methods that rely heavily on expensive geophysical equipment and aggressive land disruption, insect-based mapping uses low-tech tools and high observation skills. And for those who master this approach, the payoff can be extraordinary. A typical toolkit for this method is remarkably simple, yet extremely powerful. It starts with a 20x or 30x hand lens to inspect soil particles for signs of mineralization. A small gold pan is used to separate heavier materials in water, revealing potential gold specks or dense mineral grains. A magnet helps detect ferromagnetic particles like magnetite or pyrrhotite, both of which often occur near gold and base metal deposits. And perhaps most importantly, A basic topographic map or GPS device is used to mark colony locations and patterns, because one mound may reveal a clue, but several aligned mounds may outline a treasure. One of the most overlooked advantages of this method is its ability to detect buried mineral zones that don't show surface expressions. In many cases, gold or diamond-bearing formations are hidden under layers of alluvium, sand, or vegetation. To the untrained eye, the surface seems ordinary. But ants and termites burrow beneath those layers, sometimes reaching 2 to 5 meters deep. They bring up material from geologic horizons untouched by erosion or visible weathering, essentially offering a free window into what lies below. In one documented case, multiple termite mounds across a small ridge were found to contain unusually high concentrations of black, flaky particles. Under magnification, these flakes were identified as biotite and chlorite, minerals commonly associated with hydrothermal systems. In such systems, hot fluids from deep within the earth carry and deposit metals like gold, silver, and copper. By mapping the spread of these mounds and performing simple flotation and magnetic tests on the soil, the team identified a linear zone that matched the expected path of an ancient mineral-bearing fault. Weeks later, a formal survey confirmed elevated gold content across the exact same ridge. This pattern recognition, linking insect behavior with geological structure, is one of the most powerful aspects of the method. Because it's not about finding a nugget on the surface, it's about using biology to predict geology. And once those patterns become clear, the prospector doesn't need to guess where to dig. The Earth, through its smallest architects, is pointing directly to its hidden vaults. Another powerful indicator is soil density and color. When termites or ants construct their mounds using unusually heavy or compacted materials, there's often a reason. Minerals like hematite, magnetite, and ilmenite are significantly denser than typical sand or clay, and when found in termite soil, they suggest a source below with high mineral content. Mound material that's reddish, dark purple, or even greenish can indicate iron, copper, or chromium-rich substrates, all potential indicators of economic mineralization. These clues become even more reliable when analyzed across multiple colonies. By collecting samples from several mounds in a wide area, say, across 300 meters, and noting similarities or gradients in mineral content, a prospector can build what's known as a geochemical profile. These profiles help estimate not just if valuable minerals are present, but also where the source deposit might lie in relation to the surface patterns. One term used frequently in insect-assisted exploration is halo mapping. This refers to the detection of a geochemical halo, a ring or zone around a mineral deposit where small amounts of the target elements diffuse outward. Because ants and termites unknowingly gather material from across their territory, they often capture particles from the outer edge of such halos. By comparing samples from different locations, a prospector can triangulate the likely center of the deposit with surprising accuracy. The process is methodical but accessible. Start with visible observations. What does the mound look like? Is it unusually large? What color is the soil? Is it coarse, sticky, metallic? Then move to sampling. Collect small amounts of soil from the outer layers and central core of the mound. Wash them, dry them, inspect for particles that shimmer or sink quickly. Use a magnet. Record everything. As your map of colonies grows, so does your understanding of the subsurface. It's like assembling a puzzle without ever breaking the surface of the ground. One particularly exciting trend is the use of drones to assist in colony mapping. With aerial imaging, it's now possible to identify dozens or even hundreds of mounds across a landscape, then match those images with satellite data on topography and drainage. This cross-referencing allows for precise targeting without disturbing a single plant or animal. It's efficient, it's eco-friendly, and in many cases, it's more accurate than traditional exploration methods. As more prospectors around the world begin applying these techniques, a clear truth is emerging. Gold, diamonds, and rare minerals are not just buried beneath mountains or locked away in deep caves. They are also quietly signaled by nature itself. The ground is never truly silent. Through the rhythmic movements of insects, it whispers its hidden wealth to those willing to listen. Turning this knowledge into real discovery begins with the soil. For those seeking gold, several non-toxic chemical field kits now allow for rapid detection of microscopic particles. These tests work by applying a reagent to soil samples, which reacts with gold and reveals its presence through color changes. When performed on mound material, especially from termites or ants known to tunnel deeply, this method can confirm whether a location is worth further exploration. without breaking the earth. But gold is just one part of the story. The same mounds that hide gold traces often carry what geologists call indicator minerals, substances like garnet, ilmenite, magnetite, and pyrope that point toward potential diamond-bearing rock. By inspecting soil for these crystals, either visually with a loupe or through basic sedimentation techniques, a prospector can detect the presence of kimberlite or lamproite pipes, two of the most important volcanic conduits for diamond formation. This layered approach increases accuracy. First, observe mound characteristics, color, density, shape, and location. Then conduct simple magnetism and panning tests. Finally, analyze chemical and mineral content. Each step adds confidence, each clue builds on the last, and over time, the land begins to reveal its pattern, not in straight lines or obvious signs, but in a subtle mosaic only visible to those who have learned how to see. Throughout this journey, perhaps the most important lesson is this: the power of discovery lies not in force, but in understanding. For generations, mining has been a story of conquering nature. But what if the next chapter is one of cooperation? What if the real explorers are those who let the earth lead the way? In one story we covered, a small team in an undeveloped region used termite mound analysis alone to identify a corridor of mineralization that led to copper and gold. No machines, no invasive surveys, just data, discipline, and observation. The results? A confirmed strike that later became the basis for a community-led micromining project. And that's the beauty of this method: it scales. It works in vast, unexplored regions, and it works in a backyard. It works for governments, and it works for independent seekers. Because nature doesn't discriminate, it speaks to everyone. The question is, who's listening? Even now, researchers are exploring whether other soil dwellers like burrowing beetles, ground wasps, or even certain species of worms might carry similar clues about hidden minerals. New research is being published every year, confirming what many indigenous communities have understood for centuries: that the smallest creatures can reveal the greatest secrets. As we close this chapter of the journey, the next step is yours. Whether you're a seasoned prospector or someone just curious about the hidden patterns of the land, know this: there is treasure beneath your feet, not just in value, but in knowledge, in learning how to read the earth and discovering that the greatest technology we may ever need already exists in nature. If this exploration sparked your curiosity, if you learned something new, or if you want to keep following these natural paths to uncovering what others miss, remember, the land remembers, and together, we're learning to listen.